So, welcome to lecture 5 of Foundation of Mathematics and Philosophy. In the lecture 4, uh, we talked about backtracking definitions a little bit, but we left off with the idea that it already uses the language of set theory and logic and it gets unnecessarily complicated. So, in this lecture, in lecture 5, we will try to do two things. The first one is define what is backtracking process, which we already know, and I will explain it a little bit while defining it. And that definition we use, it will not be formal, but it will be more formal than what we have discussed in earlier part 1, 2, 3. And then we will try to define backtracking using a diagram, which is much simpler because the diagram is just a pictorial representation form and it doesn't use the language of set theory and logic that is unnecessarily complicated. And then we will move to Euclidean geometry. Once again, we will visit it and see what are the presumptions in the construction of Euclidean geometry. So let's begin. So the idea we talked about is backtracking. Backtracking was like let's consider a fact. Let's say this is a fact n. Then we try to backtrack that what are the assumptions made to assert this fact n, and we find that maybe it relies on fact n minus 1, but we can do same thing for this and we get maybe f n minus 2, and we go on and on, right, until we stop at some fact, say 0, right, or let's say fact 1. This is fact 1. So we stop here because these are the most primitive it could be primitive object definitions and the most primitive assumptions that we cannot backtrack it further, and that will be the end. For example, we got when we were trying to backtrack while proving the sum of angle of triangle 180 degree, we got at the end of this fact: point has no parts. This was the fact, and we cannot go further because that is the primitive object. We accept this, right? So this is the chain. It's a chain that is tracking backward, right? And we said these facts are what? These facts are called proposition. You can call it proposition because now we are trying to define backtracking, and so to make it formally, we need to understand what proposition is, because we are going to use theoretical language a little bit. So what is a proposition? A proposition is a statement. Proposition is a statement, and there is one more required, that this statement, the requirement is that it should have truth value. Truth value means either this statement is true or this statement is false, right? For example, given a line and a point, let's say this is a line L, this is a point P. This point either lies on this line or it does not lie on this line, right? It's a proposition. It is either true or false. Similarly, if given a two line on the plane, this is the plane, this notebook is a plane, here is a two line. Now this line either intersect each other or they don't intersect each other. So it is either true or false, right? So proposition is like true or false. For example, 2 and 2 makes 4. Either it is true or false, right? Sum of angle of triangle is more than 180 degree. It is either true or false. right? So every proposition has a truth value. Either it is true or it is false. And that statement that can have two values, which is true or false, then that is called proposition. There are two kinds of proposition. The one is atomic proposition. The name itself says atomic. It means it cannot be further break down. Like here, point has no parts. It is atomic proposition. So atomic proposition means the most simplest kind of proposition. Simplest kind. By simplest I mean simplest kind of proposition. Simplest means can't be further broken down. Right? Means you cannot. What is broken down? That we will get understand what does it mean. So we have atomic proposition, and then we have compound proposition. Compound proposition. What is compound proposition? It is compound proposition contains more than one atomic proposition. We talked about this in lecture 4. What is atomic proposition and what is compound proposition? Compound propositions are made using words like and, but, etc. Right? You take two atomic proposition, and connect them using these words. That becomes a compound proposition. Right? Now, some statement can be compound proposition, some of fact can be atomic proposition. Right? Now consider this. Now take a compound proposition. Take a compound proposition. Let P equal to compound proposition. And since it is a compound proposition, it can contain more than one atomic proposition, right? So let's collect all those atomic proposition that is used to construct this compound proposition. So we have P1 atomic proposition, P2 atomic proposition, P3, ... and so on. It is a set. So what is set? We don't want to go deep into it, but set is, for now we can say it is collection of well-defined object. We can say collection of objects for now. So we have this set P. P is the compound proposition, and this compound proposition is constructed using these kind of atomic propositions, right? Now, so we take a fact. For example, this compound proposition could be given a line and a point. There is exactly one line passing through this point that will be parallel to this line, parallel to M, L. This is a compound proposition. Why compound proposition? Because we backtracked it and we found it relies on so many facts. So if P is this one, then all those facts that has been used to assert this fact are these facts. This P1, P2, P3 and so on. Right? So these P1, P2, P3, ... and Pn, it is not isolated. You see? Even they are atomic, they are not isolated. They are interdependent. One does not exist without another. Without, let's say P1 is definition of point and P2 is definition of line. Then without definition of point, you cannot have line. It means there is a connection, there is a relation, right? So what is backtracking? Backtracking is, I consider a proposition P, compound proposition, which is a set of atomic proposition, and then there is a relation on this P1, P2, P3, ... and so on. There is a relation between them, some sort of relation, right? And there is a order in a sense. Without point you cannot get line, without line you cannot get plane, and so on. There is a relation, this kind of relation. this interdependency, this sort of relation we have embedded into this set, right? So it is not just a set, it is a structure. We will make clear what we mean by structure later, right? So any statement which is not compound, which is not atomic, we can form a structure among it, right? There is a structure sitting there. Structure means, for now I can say, take a set and some sort of algebraic operation or relation, and we put together, it becomes a structure. We'll talk about this later. I don't want to make complicated here, but for now we can call it just a set here. So backtracking is a process where take a compound proposition and collect all those atomic propositions that has been used to construct this compound proposition, and then we find the relation between these atomic propositions. We backtrack it, and then we can see there is a relation between this P1, P2, P3 and so on, and this is called backtracking process, right? Now in a diagram you can say, here is a compound proposition, and suppose we backtracked it and we found that this compound proposition is dependent on another compound proposition, let's say P1, and then we find out that this P1 is we are backtracking, this P1 is dependent on another, let's say P2 and P3, two propositions, and then we found that P3 is dependent on P4, right? And then this is also on P4. So this is the process of backtracking. So we don't have to take this kind of language structure and the set, and these are very abstract for now. We just can see it from this diagram. It's kind of tree diagram, right? So this is what happening. We are backtracking the propositions. This is dependent on this is dependent on P2 and P3, P3 is dependent on P4, P2 is dependent on P4, maybe P4 is dependent on P5. That's how it goes. For example, let's consider a proposition P equal to, given a line and a point, given a line L and a point P, there is exactly one line passing through this point P, call it M, that will be parallel to this line L. It's a proposition. So let's call it P. Now this proposition is dependent on what? It's dependent on one more proposition, that is, given a point you can pass infinite line. So this is proposition 1. But this is also dependent on another proposition, which is a line is a breadthless length, it has no breadth, and this is dependent on idea that there is a point which has no parts. So you can see here is our proposition P, this one, and we backtrack it and we found that it depends on here is a proposition and it depends on two facts. First, for this there must exist this, right, which is let's say P1 through a given line, through a given point, infinite line can pass, and then there is a concept of line which is P2, right, because this is dependent on this and this, without this and this you cannot form this, and then this P2 is and then this P1 this P2 is dependent on, let's say, P3, and P1 is also dependent on P3. So this is how we backtracking it, the process. See, this is backtracking, right? Now we are going to talk about, we're talking about here. So we'll talk here, and this is the idea of, so we are talking Euclidean geometry. Now consider this few statement. 1. What are we going to talk about? I don't want to say it right now. You will get clear from what I'm trying to say. So first, see this statement. If there are two lines L and M on a plane, let's say P, not say P, just on a plane, then either, what it's trying to say, if there are two lines L and M on a plane, then either L and M, these two lines, intersect one another or they don't. What does this statement mean? It means given a plane, here is a plane, this is a plane, a two-dimensional plane. We are talking everything on two dimension. So here is a two-dimensional plane. It says given a line L, let's say there is a line L, and given a line, let's say M, here is a M. So it's saying given two line L and M on a plane, here is two line on this plane, either L and M intersect, means either L and M going to cut one another at some point, intersect or meet, we can say, or they don't, right? There are only two options. Either we extend this line and we see, yes, here they are going to intersect. Or if there are two lines L and M given, they don't intersect here. They will never intersect. This is parallel. So there are only two options. Either they intersect or they don't. So it is either, so we can say this statement is either true or false. True means we can represent true by 1 or false by 0, right? This is just a notation. So this statement, if there are two lines L and M given on a plane, then either L and M intersect one another or they don't. So it is either 1 or 0, true or false. Another statement, see the example. Given a line, let's say given a line L and a point P, either P, this point, lies on line L or it doesn't. What does it mean? It says, let's say here is a plane and there is a line given and there is a point given. So this statement is going to, what's the statement trying to say? Either this point lies on this line or they don't. In this case, this point does not lie on this line. Or given a line and a point, let's say P, now this point lies on this line because we can extend this line and we can see this point P belongs to this line. I mean this point P lies on this line L. So there is also, this statement is also true or false. True means 1 or 0, false, right? So these are some sort of a statement which has two values, either 1 or 0, means either true or false. Here, true or false, right? Now, what are we going to say here is that Euclidean geometry, this is a very important statement. This is very important statement. Euclidean geometry somehow already presume not only those definitions of point, line, plane, right? And those all kind of definitions we saw through backtracking. Not only that, they don't only assume those primitive objects, they also assume one more thing, which is logic. This is very important. And that logic is based on the idea that given any statement, it can be either true or false. We have to be very careful here. What is trying to say? Euclidean geometry does not only assume those definitions of point, line and all kind of those stops and all the axioms of geometry. No. Those are different kind of assumptions. The another assumption is itself the idea that any statement can be either true or false. And now we will, in the next lecture, we will extend this idea and see what does it mean, right? So for now we will stop here.